Okay, good morning, all of you. Welcome to this lecture of refrigeration and air conditioning. So, like, we are now in the chapter of psychrometry. So, yesterday in the evening lecture, I have dictated some of the properties of the moist air. Okay, but before that, we will take a quick revision of what we have learned to this point. So, we started with atmospheric air. So, as we all know, atmospheric air is a mixture of gases plus water vapor plus dust particles. So if you take only the gases, this part, so if you take this as a domain, if you take only mixture of gases, so this will be your dry air. If you mix with the water vapor, so this will be your moist air. Okay. So this two will give you moist air. If you mix this with the dust particles and fumes, that will be called as atmospheric air. So up to some level from the ground, so like around 10 kilometers from mean sea level, you will get all this mixture. But as the level from the ground mean sea level increases, the concentration of dust particles and water vapor decreases, and at some level around about 10 kilometers from the ground, so that you will get only dry air, right? So next we saw the moist air. So what you see table here, this is the table for dry air. So these are the constituents of a dry air. We have oxygen, we have nitrogen, argon, carbon dioxide. Oxygen is 21%, nitrogen it is 78%, and then we have 1% argon and other gases. Okay. Then if you take the mixture of dry air plus moisture, dry air and moisture, so this will give you moist air. Okay. Then we came to saturated air. Saturated air is a concept. So in this, what happens when the air is saturated? Air has reached its maximum capacity of holding water vapors. And if it exceeds this, then water will condense, or it will convert into liquid droplets. Okay, so there will be like a dew formation and what you say rain. So these are the effect of saturated air. Air becomes saturated, and then water droplets starts falling. Okay, so for this you can take example of a sponge. The sponge we use to clean the surfaces, wet surfaces. So a sponge has some capacity of holding water. So if it exceeds this capacity of holding water, what will happen? Water will start dripping from that sponge. Okay, so that sponge has some capacity of holding water content. If it exceeds this capacity, water will start dripping. So this is like analogy between saturated air and sponge. Okay. Then we have seen Dalton's law partial pressure. So if you take a mixture of gas A, gas B, and there is a mixture. So if you take a total pressure in this system, so total pressure in the mixture, it is the summation of partial pressure of gas A plus partial pressure of gas B. Okay, so this is the Dalton's law of partial pressure. So this is applicable to our moist air also. So moist air is a mixture of dry air plus moisture. So in that case, if you take total mixture, okay. So wait, I have call. Okay, so this is about Dalton's law of partial pressure. Then next we have seen the temperature. So in temperatures, we have three temperature values. First is a dBT, that is a dry bulb temperature. So it is a temperature what we measure with a normal thermometer. Then we have a wet bulb temperature, that is a WBT. WBT is the effect of evaporation of water from the surface of a thermometer. So if you cover the thermometer with a wet cloth, so there will be evaporation of water. It will there will be transfer of it, and there will be reduction of temperature. So what you get that reduced temperature, that is nothing but a wet bulb temperature. The third is dew point temperature. Dew point temperature is referred to saturation air. So the minimum temperature below which there is a condensation of water vapor. So that temperature what we are referring is at a dew point temperature or DPT. Okay. So these are the instruments to measure this dry bulb temperature and wet bulb temperature. Ring psychrometer is a conventional work. Now we have a digital psychrometers. Okay. In last lecture, we have seen this concept of saturated vapor pressure. So in this case, I have showed you that saturated partial pressure is nothing but it is a partial pressure of water vapor at dry bulb temperature. That means what is happening. So if you take example of atmospheric air around you right now, so in that case, what air is not saturated. Okay, so right now air is not saturated. So water has not reached to its saturated partial pressure. So when water will reach to its saturated partial pressure, that time we can say air is saturated. Okay. So we have seen this formula for saturated vapor pressure. This is the formula. In last lecture, I have showed you how to uh, represent this formula in a Excel file. Okay. So I'll just quickly show you what I'm saying. So those who are new, they can relate to this. So yesterday I showed you how we can plot that data on Excel. So I have one column of temperature. I have taken some values starting from 2 degrees Celsius, or in Kelvin we can say 275 Kelvin, then up to 315. Then next is a log of P saturated. Okay, so I have used here formula. So if you see here, I have this formula I have taken from that PPT. Okay, so that formula I have applied here, then I will get a log of P. If I take inverse of log or exponential of P, so I will get a saturated pressure value. This is in kilopascal. Okay. So like way I can plot various values, and then I have drawn one graph here. Okay, so this is not part of your syllabus, but Excel, like I said yesterday, Excel, PowerPoint, and Word, these are very important office skills you should know. So when you get this data, you can draw a graph. So there is a feature of inserting a graph. Then on x-axis you have temperature values, on y-axis you have this pressure values in kilopascal, and then you can get the graph. Okay. So you can interpret from this graph that as the temperature value increases, this pressure values or the saturated pressure, saturated partial pressure values also increases. Okay, so this is so in like आता ह्याचा ऍक्च्युअल वर्ड मध्ये मिनिंग काय, जसं तुम्ही समर मध्ये एखादी केस घेतली, समर मध्ये टेम्परेचर अराउंड 40 डिग्री सेल्सियस असतं. 40 डिग्री सेल्सियस मीन्स इट इज अराउंड 315 Kelvin. So in that 350 Kelvin, saturated partial pressure is very high. That means there are very less chances that air will be saturated. But if you see winter or rainy season, in that case, temperature is lower. It is around 20 or 25 degrees Celsius, or I can say 300 Kelvin. So in 300 Kelvin, saturated partial pressure is lower. That means there are higher chances of air getting saturated. That means there are higher chances of rain. ओके, जर लो टेम्परेचर असेल तर त्यामध्ये सॅच्युरेटेड पार्शियल प्रेशर कमी राहतं, त्यामुळे तुमचे चान्सेस जास्त असतात पाऊस पडण्याचे किंवा एअर सॅच्युरेटेड होण्याचे. ओके, सो दिस इज द रिलेशन बिटवीन सॅच्युरेटेड पार्शियल प्रेशर अँड टेम्परेचर. Okay, so you can also draw this graph. So this graph I have drawn from using this formula. So you can do the same. You can take various temperature values, and from that you can you have to just put a formula for this saturated partial pressure, and then you will get the values for various values of the temperature. Okay, then you can get the graph as like I showed you in the Excel file. Okay, so these are the constants, and this, when you put this constant, then you will get the value of the saturated vapor pressure. Okay, so this is like a regression equation. This is obtained from various experiment. तर हे तुम्ही मे बी तुमच्या हायस्कूल मध्ये किंवा फर्स्ट इयर सेकंड इयर मध्ये केलं असेल. आपण एखादा एक्सपेरिमेंट करतो, परत त्या व्हॅल्यूज आपण एक्स आणि वायच्या ग्राफवर पॉइंट्स प्लॉट करतो. आता पॉइंट्स प्लॉट केल्यानंतर आपण काय करतो, आपल्याला जर लिनियर इक्वेशन पाहिजे असेल तर वी गेट अ लाईन विच बेस्ट फिटेड फॉर द पॉइंट्स. त्या पॉइंट्स मधून जाणार एक आपण लाईन काढतो. Then we'll get the equation as y is equal to mx plus c. Okay, so our objective here is to find out the slope of the line. Okay, जर तुम्हाला एक्सपेरिमेंट मध्ये असे जर पॉइंट्स मिळाले तर इट इज नॉट or it is clear that the line will not pass through it, then you have to draw the curve, then you have to go for non-linear equation. So like it will be what, x square plus bx plus c. In that case you have to find out the constant values of a, b and C. So likewise, Astoria has done that experiments and he has obtained, or it has obtained this equation. Okay, and these are the constant values. So this is again not part of the syllabus, but this is a important concept, saturated vapor pressure. Okay. Then I showed you in last lecture, this is the table. So this is a table of temperature versus saturated vapor pressure. So as you can see, if I take lower temperature of -7 degrees Celsius, you can see saturated vapor pressure here it is a 3.7. As the temperature increases, so suppose it goes to +7, at 7 it is a 10.3. So as you can see, as the temperature is increasing, saturation vapor pressure is also increasing. Okay. So vapor pressure is nothing but the partial pressure of water vapor. Saturation vapor pressure means the pressure at which the water will start to condensate, in simple words. Then there is this graph they have obtained. So similar graph we have obtained in our Excel file. Okay. Then this was the last concept we discussed in last lecture. So relative humidity. So relative humidity is defined as the ratio of mole fraction of water vapor in moist air to the mole fraction of water vapor in saturated air at the same temperature and pressure. Okay. So using perfect gas equation, we can show that this relative humidity is equal to partial pressure of water vapor. This means what is current partial pressure of water vapor. So if suppose in this atmospheric air, like you are now sitting, तुम्ही ज्या एअर मध्ये सध्या आहे प्रेझेंट त्यामध्ये सपोज पार्शियल प्रेशर वॉटर वेपर हे आहे 25 मिलीबार. ओके, 25 मिलीबार. And saturation pressure of pure water vapor at the same temperature. Now suppose temperature now here it is 30 degrees Celsius or 32 degrees Celsius. So you can see here. So you suppose if I take temperature of 32 degrees Celsius, right? So I have to look into table what is this saturation vapor pressure. So here saturation vapor pressure is 48.1. So what I will do now, I will divide this 25 divided by 48. Okay, understood? So I have to take its partial pressure 25. I assume one value. Then for a given temperature, I have to take its saturation vapor pressure. So when you divide 25 by 48, I don't know how much it will give, but it will give you some 0.5 value, right? So this 0.5 is nothing but your relative humidity. But in general, this RH value we give in terms of percentage. So 0.5 means this will be 50% relative humidity, 50% RH. Okay, I hope you understood. So relative humidity is normally expressed as a percentage. When phi is 100%, the air is saturated. That means phi is 1 or 100%. That means air is saturated. Okay. So that was about the last lecture. We stopped at the relative humidity. Today we'll continue from humidity ratio. Now, humidity ratio is very important concept if you want to draw the psychrometric chart. Okay. So humidity ratio or specific humidity, we generally term it as a W. Here it is shown W as a capital, but in general we take it as a small w. So the humidity ratio or specific humidity is the mass of water associated with each kilogram of dry air. So as a definition suggests, we generally write this as a kg per kg of dry air. Okay. So if you take a mixture of air, this atmospheric air is a mixture of dry air, okay, and it is a mixture of water vapors. So that is what we call it as a moist air. Okay, so this is a moist air. So moist air is a mixture of dry air and water vapor. So it has some mass in kg. It has some mass in kg. If you take the kg or the mass of water vapor per kg of the dry air, that ratio is nothing but the humidity ratio. Okay, so kg of water associated with kg of dry air. So that ratio is humidity ratio. Okay, so assuming both water vapor and dry air to be perfect gases, the humidity ratio is given by. So there is a formula for this. So this humidity ratio is equal to kg of water vapor divided by kg of dry air. If I use the ideal gas equation, this mass we can write it as a PV into volume divided by R into T. So because the ideal gas equation is PV is equal to MRT. So if I take only M on one side, so this will be obviously this will be PV divided by RT. Okay. So similar equation they have applied for the water vapor, and similarly for dry air, this will be PV divided by RT. So in this case, the temperature we can cancel it because it is a common. Volume we can cancel because it is a common. Then this divided by this. So this way we can get it. So this we can solve it as a, so V will get cancelled, T will get cancelled. This PV divided by PA. Okay, so this will be like PV into RA divided by PA into RA. So this PA we can replace by PT, total pressure, minus vapor pressure of water vapor. So PA is dry, partial pressure of dry air. Partial pressure of dry air can be replaced by total pressure in the system minus partial pressure of the water vapor. Total pressure also we can write it as a PB. So PB means barometric pressure. Okay, so these two are same. We can take a total pressure or we can take a barometric pressure. So it is generally written as PB minus PV. Okay. So substituting the values of gas constant of water vapor and air in RV and RA in our equation, the humidity ratio is given by. Okay, so we have equation here PV divided by PT minus PV into RA by RV. Okay, so for air, we already know what is the gas constant. Here it is a 287 joule per kg Kelvin. Again, for water vapor, so for water, we know that value. So I have taken from internet, it is a 461 joule per kg Kelvin. Okay. So if you substitute values there, okay, in this equation, so what will happen here? So it will be PV divided by RV is 461 divided by PT, or we can take PB minus PV divided by 287. Okay. So you have to just solve this equation. So this will be what? This equation will remain same like at is it. So it will be like 287 divided by 461. And this values comes out to be around 0.622. Okay. So in this equation, I have just substituted the gas constant value. Then I will get this equation. So this constant will be there 0.622 into PV divided by PT minus PB. PT or PB, one and the same. You can take PB as a barometric pressure or you can take total pressure. So humidity ratio is equal to 0.622 into PB. PB is nothing but a partial pressure of water vapor divided by total pressure minus partial pressure of water vapor. So this is nothing but partial pressure of dry air. Okay, so humidity ratio is equal to 0.622 into partial pressure of water vapor divided by partial pressure of dry air. Okay, so write down the formula for humidity ratio. This is very important formula. There are numericals based on this formula. Okay, completed. So this is about humidity ratio. So we have seen the properties of moisture as first we have seen temperature, dBT, WBT, dPT. Then we have seen saturated vapor pressure. Then we have seen relative humidity. So right now we have seen the humidity ratio. So there are some other important properties that also we'll see. Okay, so next is the relation between dPT and RH. So dPT is dew point temperature and relative humidity is RH. So there is an equation. So an approximate equation for dew point temperature is given by dew point temperature is equal to. So this equation it is given. It is a relation between dew point temperature and relative humidity. Okay. So this is equation given for the dew point temperature and relative humidity. So what you can interpret from this is that, so if you take RH as 1, so there is a, suppose air is now saturated. Air is saturated means there is a RH of 100%, or we can take RH is equal to phi is equal to 1. If I put phi is equal to 1 in this equation, what will happen? So this equation will reduce to dew point temperature is equal to 4030 into dry bulb temperature. So this is your choice. So whatever temperature you want, you can take divided by 4030 minus dBT plus 235 into ln1. So ln1, as you know, this reduces to 0 minus 235. Okay, so as this reduces to 0, this whole term will reduce to 0. So this 4030 will cancel. So what will remain here? It is dBT plus 235 minus 235. This will again cancel each other. This will be equal to dBT. So what we can say here, when there is a 100% relative humidity, your dew point temperature is equal to your dry bulb temperature. Okay, 100% relative humidity means air is saturated, water has reached to its saturation vapor pressure, water is about to condensate. In that case, what happens? Your dew point temperature is equal to dry bulb temperature. Okay, so this is the relation between dew point temperature and relative humidity. So you can write it down. So it says where phi is the relative humidity in fraction and dBT and dPT are in degrees Celsius. Okay. So I'll erase this. So the dew point temperature is the saturation temperature corresponding to the vapor pressure of the water vapor. It can be obtained from the steam tables. So in steam tables, as you know, there is a temperature table and pressure table. So in temperature table, the whatever temperature values are given, that those are nothing but the saturation temperature values. In pressure tables, whatever values of pressure are given, that is nothing but the saturation pressure values. So if you take vapor pressure of water vapor, so that table I have just show you, temperature versus saturated vapor pressure. So corresponding to that partial pressure of water vapor, whatever saturation temperature it is there, that is nothing but the dew point temperature. Okay. And the last but not the least, degree of saturation. So degree of saturation is given by the mu. So degree of saturation is the ratio of humidity ratio W to the humidity ratio of a saturated mixture WS at the same temperature and pressure. Okay. So if you take a mixture of moist air, it will give you some value of humidity ratio. Humidity ratio is the ratio of mass of water vapor to the mass of dry air. Then if you take the another case of the same mixture where air is saturated, so saturated air, in that case, if you take the humidity ratio, again the mass of water vapor to mass of the dry air, so that will be Ws. If you take the ratio of these two, W divided by Ws, so that is nothing but the degree of saturation. Okay, simple definition. So degree of saturation is the ratio of humidity ratio W to the humidity ratio of saturated mixture Ws at the same temperature and pressure. So this is given by mu is equal to W divided by Ws at the same temperature and pressure. Okay, so after degree of saturation, next concept we have here one more concept. I think that was not the last. So we have one more concept here, enthalpy. Enthalpy, as you know, this is the energy in flow. So for a closed system and non-flow system, we have internal energy. If you take the example of steady flow, steady and transient flow. So in that case, if there is a flow, in that case, we have to deal with the enthalpy. Enthalpy is the energy in flow. Okay. So if you take the enthalpy of moist air, so what it says here, enthalpy of moist air is the sum of enthalpy of dry air and enthalpy of the water vapor. So this is like similar to our Dalton's law of partial pressure. So in Dalton's law, total pressure is the sum of partial pressure of dry air and partial pressure of water vapor. In case of enthalpy, it is same enthalpy of that mixture, moist air. It is the summation of enthalpy of dry air and enthalpy of water vapor. So enthalpy of moist air is given by, here it is the formula, H is equal to HA plus W into Hg. Now this is very similar to what we do in case of our pH chart. Okay, so we have studied pH chart, pressure versus enthalpy. Okay, so I hope you remember we have solved the numericals on pH chart. Okay, so if there is a one point which is in this wet region, so we have here subcooled region, we have here superheated region, here we have a wet region. If you take an enthalpy here, okay, so how you calculate the enthalpy at this point? So what you do here, so we have here HF, that is enthalpy of saturated liquid. Then we have Hg, enthalpy of saturated vapor. So H will be equal to HF plus X time. Now X is nothing but its dryness fraction into HFG. HFG is nothing but the difference between HF and Hg. So this is nothing but HFG. So this was the way how we obtained the enthalpy of a wet mixture. And moist air is nothing but a wet mixture. Okay. So in that case, enthalpy will be equal to HA, enthalpy of a dry air, plus W, that is the humidity ratio, into enthalpy of water vapor. Okay. So this way we can obtain the total enthalpy. Now this HA we can replace with Cp into T, Cp for air into its dry bulb temperature, into W into in bracket. So is Hg, they have replaced with HFG, that is the enthalpy of saturated liquid water, plus CPW, this is specific heat for water, into T means that dry bulb temperature. Okay, so this is a formula for enthalpy of moist air, Cpt into W into in bracket HFG plus CPW into T. Now in this case you can see Cp, that is the specific heat of air, that is a constant. Then HFG, that is a latent heat of water, that is also a constant. CPW, that is the specific heat of water, that is also constant. So we have this constant term, and variable terms here it is temperature and humidity ratio. Okay. So if I put the values of this constant, that is the specific heat of air, specific heat of water, then latent heat of water, then I will get this equation. So H is equal to 1.005 T. So we know that specific heat of dry air it is 1.005. So H is equal to 1.005 T plus W into 2501. So 2501 is the latent heat of water plus 1.88. So that specific heat of water vapor, they have taken it as 1.88 into T. T is the dry bulb temperature. Okay, so this is a relation for our equation for the enthalpy. Enthalpy, you can say here it is a function of temperature and humidity ratios. Okay, so all these equations are very important if you want to draw the psychrometric chart. So in upcoming slides, I will start to draw the psychrometric chart. In that case, we have to use these equations. So write down. Okay, so I hope you have written the equation. So after enthalpy of moist air, we have humid specific heat. So we know the values of specific heat for dry air. We know those values of specific heat for water. But what about the humid air or the moist air? So from the equation of enthalpy of moist air, the humid specific heat of moist air can be written as. So this is the specific heat of moist air. This is equal to Cp. Cp is nothing but the specific heat of dry air plus W, that is nothing but the humidity ratio, into CPW. CPW is the specific heat of the water vapor. Okay. So this is the equation for specific heat of humid air or the moist air. Okay. So I will read this. Since the second term in the above equation is W into CPW is very small, so this term, so this term is very negligible, is very small compared to the first term. For all practical purposes, the humid specific heat of moist air, that is the CPM, can be taken as 1.0216 kilojoule per kg of dry air Kelvin. Okay, specific heat, you know that generally we write it as a kilojoule per kg Kelvin. So in case of our moist air, it will be like 1.0216 kilojoule per kg of dry air into Kelvin. Okay. So remember this value. This is the specific heat of moist air, that is 1.0216 kilojoule per kg of dry air. So I think there is some connection is lost. I will try to reconnect. Okay, so that is about the humidity specific heat of moist air. So generally we take this constant value as 1.0126 kilojoule per kg of dry air, right? Okay, so we have seen up to this point, we have seen temperature, we have seen saturated vapor pressure, relative humidity, specific humidity ratio or humidity ratio. Then we have seen enthalpy of moist air. Then we have seen humidity specific heat. Next point here, it is the specific volume. Okay, specific volume is defined as the number of cubic meters of moist air per kilogram of dry air. So as the name suggests, what it means. So if I take again mixture of dry air and water vapor, that is nothing but moist air. So in this case, I have dry air. So for the simplicity purpose, I am creating a imaginary wall here. But as you know, these are two mixed together. So we have dry air and we have a water vapor. In this case, if you take the volume of this dry air, now volume will be this total volume. But still, if you take only the dry gas or dry air out, and if you measure its volume, so it will be meter cube divided by kilogram of dry air. Okay, so this will be like cubic meters of moisture. Sorry, this if you take the total volume, this total volume of the mixture, this is the total volume meter cube. If you take this volume in meter cube divided by kilogram of dry air, so this ratio is nothing but a specific volume. Okay, so V is equal to total volume of the system divided by kg of dry air. In this case, they have replaced this with this equation. V is equal to RT divided by P, because it is per kg. So that case, mass will not be there. Okay, so we know that the ideal gas equation is equal to PV is equal to MRT, and the V will be equal to P divided by MRT. But if you are taking this as a per kg, in that case the mass will be 1. So it will be simply P will be in denominator. So this will be equal to RT divided by P. If it is a specific, means per kg, if you take the value, that case mass will not be there. So here they have taken the similarly, they have taken the RT, RAT, that means gas constant of air, into temperature, that means this is a dry bulb temperature, divided by the pressure, that means atmospheric or the air pressure. Okay, so this air pressure, this is nothing but the partial pressure of dry air. This can be replaced by total pressure or the barometric pressure minus partial pressure of water vapor. So they have obtained this equation. Okay. In this case, this RA you can replace with its value, that is a 287 joule per kg Kelvin, and that way you can simplify this equation. So this equation again can be simplified it as a 287 temperature divided by PT minus PV. Okay. So this is a specific volume. All these terms what I explained you today, those will be there on the psychrometric chart. Okay. So up to this point, we have covered almost all the properties of the moist air, starting from the temperature to the saturated vapor pressure. Then we have seen the humid specific heat. We have seen the relative humidity. We have seen the humidity ratio. Just now we have seen the specific volume. So all these properties will be there on the psychrometric chart. So we'll see a small glimpse of the psychrometric chart, and in next lecture, I will tell you how to draw the psychrometric chart. Okay. So psychrometric chart, okay, this is a very important concept in if you are dealing with the air conditioning system, because all the systems, so there are various types like cooling and dehumidification, cooling and humidification, heating, cooling, all these processes in the air conditioning system that can be showed on the psychrometric chart. So okay, so if you are going to one system, air conditioning system, you must know what you are trying to do. Okay, so you will design a system for cooling purpose, but it is cooling as well as it is removing the moisture, which is not necessary. So that will affect your performance. Okay, so all the processes inside air conditioning system are first studied on the psychrometric chart. Then it is seen that if you are getting the same result as we want, then that system is manufactured. Okay, so psychrometric chart are very foundation of designing an air conditioning system. All the properties like temperature, humidity ratio, specific volume, those all will be studied on the psychrometric chart. Okay. So previously they used to refer this on-paper psychrometric chart, which was provided by Carrier or the ASHRAE. Nowadays they go for the digital psychrometric chart. Okay, so it is like one code is provided. On that code, if you put the value of dry bulb temperature, RH values, automatically it will give you other values. Okay, so those softwares are also there. Mainly what they are using, the Carrier psychrometric chart. It is available free. You can also download and install it. On that psychrometric chart, if you select on any point, that point will give you all the details of the psychrometric properties like dry bulb temperature, wet bulb temperature. All those properties will be provided by the software. So this is in modern age. Previously they were used to refer the on paper psychrometric chart. Okay, so I will read it one by one. So a psychrometric chart graphically represents the thermodynamic properties of moist air. Okay, the standard psychrometric charts are bounded by the dry bulb temperature line, abscissa, that means the x-axis in our case, so and the vapor pressure or the humidity ratio on the ordinate. Okay, so on the horizontal here we have a dry bulb temperature. So on the y-axis we have a humidity ratio. So this is a kilogram per kg of dry air. So the left hand side of the psychrometric chart is bounded by the saturation line. Okay, so we have one line at the bottom, that is x-axis. Then we have y-axis, and there is another curve. So what you see here, this end curve. Okay, this end curve is nothing but the saturation line. Okay. So in general, if I want to draw a psychrometric chart, first I have to draw this abscissa, that is a dry bulb temperature. Then I have to draw its ordinate. Okay, then I have to draw its saturation line. So this is the saturation line. So this is the first figure you should draw if you want to draw the psychrometric chart. After drawing this psychrometric chart, then you can show various processes. Okay, so you have to draw first dry bulb temperature line, then you have to draw the specific humidity line, that is a vertical line, and then you have to draw the saturation line. Saturation line means their relative humidity will be 100%. Okay, so the left hand side of the psychrometric chart is bounded by the saturation line. Okay, the psychrometric charts are readily available for the standard barometric pressure of 101.325. So this is the atmospheric pressure at sea level and for normal temperature 0 to 50 degrees Celsius. Okay, so we have a range of dry bulb temperature at 0 to 50 degrees Celsius and chart at 101.325 kilopascal. So don't worry, for various processes atmospheric pressure हे असतं स्टँडर्ड, ठीक आहे, पण atmospheric जर चेंज झालं तर त्यावेळेस देखील तुम्ही सायक्रोमेट्रिक चार्ट ड्रॉ करू शकता. स्टँडर्ड जो अवेलेबल आहे तो स्टँडर्ड तो अवेलेबल आहे या प्रेशरसाठी, आपलं जे ॲटमॉस्फिअरिक प्रेशर आहे त्या प्रेशरसाठी स्टँडर्ड सायक्रोमेट्रिक चार्ट ऑलरेडी अवेलेबल आहे. But if you want to draw psychrometric chart for various barometric pressures, that also you can draw it. Just you have to take the help of equations, whatever equations we have studied today. Okay. So what you see on the right side, this is a psychrometric chart. We have a dry bulb temperature as abscissa. On ordinate, we have a humidity ratio. Then we have saturation line. Saturation line means RH will be 100%. Okay. Then what you see, these curves. So these are the relative humidity curves. Okay. Then what you see, this inclined lines, bold inclined lines. So these are the enthalpy lines, constant enthalpy lines. Okay. What you see are these dashed lines. Okay, vertical dashed lines. So vertical dashed lines, these vertical dashed lines are nothing but specific volume lines, constant specific volume lines. Okay. So this way this chart goes. But don't worry, in next lecture I will show you how to step by step draw this diagram. Then I will show you the chart provided by ASHRAE or the Carrier. Okay. So I think this is enough for today. I have given you some small glimpse of what psychrometric chart looks like. Okay. So thank you. So quickly I will take your attendance and then we can stop. So meanwhile you can ask your questions.
Digvijay sir,
Yes, sir.
Chavan sir speaking. Actually, we need to take a follow-up of gate forms.
Okay, okay.
So, um,
Sir, sir, I
how?
request you to you can take the follow.
No, not in that.
Continue.
Actually, how many
Okay.
students have filled gate form from your division in that sense? So that actually it is on urgent basis, so that I interrupted in your lecture.
No, no,
So
sir,
that
I am about to finish. So meanwhile, I will take the attendance and you can take the follow.
okay. So here 27 students are there. Out of that, how many of you have filled the gate form? So just comment in the chat box so that we will get at least some of the count. And those have filled, please send the gate form to me on my mail ID. Okay. Anna Shirsat, Rohit, Swapnil,